As introduced, I'm Sven Hebrok, and I'm going to talk about TLS session tickets with you. I'm going to briefly explain how they work, what they do in TLS, what we analyze in our paper, and what the implications of this are. So to get started, TLS, as you hopefully know, is widely used. So whenever you visit a website or do something in the internet, it is used to authenticate the server, that you talk to the correct server, and that the application data isn't modified. For this, TLS works in two steps. First, we have the handshake, where the authenticity of the server is verified, and then also a symmetric key is established using a key exchange. This key is the master secret, and from this master secret we derive the actual session keys. These are then used to actually protect your application data. However, if you do a second connection, you again have to do a full handshake and only then can transmit the application data again. And this is slow, because we again have to do public key cryptography like RSA or Diffie-Hellman, which all takes up CPU time, and also due to the way the messages are ordered in TLS takes more round trips. So we'd like to get rid of this. This is where TLS introduces session resumption. We want to get rid of the public key crypto in the handshakes and speed up the handshake. But if we don't have a key exchange anymore, we don't have any keys anymore. So we need a way to get keys. For this, we can use session tickets. The server stores the master secret in a ticket, sends it to the client, and upon resumption, the client then takes the same master secret and the ticket. The ticket is sent to the server, who can then get the master secret out of it again. Thus, we again have keys and can communicate faster without having to do a full handshake. But what is in a ticket? We cannot simply write the master secret into the ticket, because anyone observing the ticket could extract the master secret. Thus, we encrypt it. But as we don't have any shared key material, the client can't encrypt the master secret, so it is a key that is only known to the server. This key is known as the STEK, or Session Ticket Encryption Key. So the server stores this one STEK and uses it for all clients. This has the benefit if you have multiple servers, you just have to synchronize the STEK between all servers, and thus it is easier then to manage a database which would be synchronized between the servers. And the client only needs to store the master secret and the ticket if they want to resume the session at any point. So this is how tickets work, but they have issues, and this is already known. Back in 2017, Valsorda wrote a blog post summarizing some known issues of session tickets. The first point he raises is that we don't do a key exchange anymore. This was the point of session tickets, but it is an issue because now the whole secrecy relies on the ticket being secure. Because the ticket contains the master secret, and if the ticket isn't encrypted properly, everyone can read the master secret. So if the attacker has the STEK, they get the master secret and can decrypt the application data or even actively impersonate the server. Next, the same secret is reused. We reuse the same master secret, so if the attacker has the master secret of the second session, they also have the master secret of the first session and can also decrypt that, violating forward secrecy that TLS usually guarantees you. And the last issue is that the ticket is even transmitted in plain text, so the attacker doesn't need the resumption, but can decrypt the ticket in the first connection immediately and impersonate the server already there. So this is an issue. But knowing these issues, people in the wild would probably get it right and choose their STEK securely. We wouldn't be here if it was for the case. In 2022, there was a CVE in GNU TLS where they used incorrect cryptography to encrypt the session tickets. This sounds more sophisticated than it is. In reality, the key was just 0. Okay, you hear, as a security researcher, you hear about this and think of what is the status in the wild? How widespread is an issue like this? So we set out to scan servers in the wild and search for configuration issues or implementation issues like these. So when you reconnect to a server, we get a session ticket, all of that is fine. Then we take a look at the ticket we get in Wireshark, and it is complicated. How do we check whether the STEK here is now a bad STEK? The idea is we need to decrypt it and check whether we get the master secret out of it. But where do we decrypt? Which algorithm do we use? Where's the initialization vector? Where's the ciphertext? We don't know all of that. So we need to take a look at how tickets work. And this is what we've done in our paper. We first analyzed open source libraries and the standard. The standard doesn't require a specific format for tickets, and that is why we needed to look at open source libraries. We've taken a look at the algorithms used by open source libraries and looked for immediate issues. The summary is all of this looks fine and is close to the standard. Then we could continue with a large-scale analysis and scan servers in the wild. Due to time constraints, today I'm only going to talk about our results of the analysis. We performed multiple scans in our first scan, we scanned the target code top 100K hosts. And already there we found that 1.9% of hosts were vulnerable. This was because there was a bug in AWS, where the stack again was set to an all-zero value. We reported this back in 2021 and it was fixed rather fast. However, they couldn't pinpoint the exact date when this was introduced. They said it could have been introduced back in September 2020, so more than half a year earlier, due to an internal Nginx change, but they weren't absolutely sure. So this means this bug has laid dormant for at least half a year, maybe longer, maybe shorter, which is already rather significant. Then we performed more scans, and the summary is that we didn't find any authentication issues, so we also scanned for petting oracle vulnerabilities, but didn't find any, which is a good thing. We found one instance where a key stream was reused, most likely due to reused nonce, so we could again recover the key stream and recover the master secret, and we found a lot of weak keys. As mentioned, we found 0 keys. But we've also found this instance where the key was simply counting up, and we found instances where the keys were only partially initialized, either because only the HMAC key was initialized, but the AES key was still left to 0, or only the key was initialized half of the values. So on the lower side, we can see that only half of the key was set to some value and the other half was left empty, and the initialized half was also bad. All of this implies that we might have missed some keys which were only initialized partially, like the first 3 bytes were initialized and the rest was left empty, which still isn't secure. But to test this, we would need to test our keys. Now the question arises, why wasn't this found earlier? And this is due to 2 issues. First of all, tickets still work. Even if they use a 0 stack, they work. The server can issue them, encrypt them using a weak stack, and upon resumption, they still are decrypted and the master secret is can be recovered. So no one bats an eye because it works. Secondly, it's hard to audit. Before we did it, seemingly no one audited it, so what we had to do was to try each possible key and also try several formats for each ticket and check whether we get the master secret out of it. So it is hard to audit the keys, the stacks, and hence also no one notices it. But this was all TLS 1.2, right? Balzorda back in his blog post also mentions that most issues are fixed in 1.3. So the first issue we had was that we don't have a key exchange, and this is fixed by allowing a key exchange again. Then the same secret was reused in TLS 1.2, and TLS 1.3 a different secret is used and is derived from the first master secret. So even if the second master secret is leaked, you don't get the master secret of the first session anymore, so we again have forward secrecy. And lastly, tickets aren't sent in plain text anymore, but are sent protected by the session keys. So 1.3 improves a lot of things, but still isn't perfect. If an attacker still has the stack, because the key exchange is optional, and if the key exchange isn't performed, they can still decrypt the application data. Then TLS 1.3 introduced zero RTT data, which are only protected by the secret in the ticket, and thus an attacker knowing the stack can always read the zero RTT data. And it is still possible to always impersonate the server because the authenticity of the server relies on the ticket being secure. And even if in addition to that, TLS 1.2 is still widely used. So 1.3 unfortunately isn't the solution to all of these issues. To conclude, we've seen that 0 isn't a secure key. We've known that before, but we've seen that it's still used in the wild. We've seen that TLS tickets can undermine security guarantees like forward secrecy and actually do undermine this in the wild because they might be configured wrong or there is a bug in the software. So we think that there's a hidden danger in cryptography shortcuts because we got rid of the key exchange and the authentication of the server and rely on the tickets. And this is an issue because we had secure measures and now with the session tickets we shortcut them and seemingly this can break easily. Also, this breaks silently. The ticket still worked and nobody noticed, so this is an issue and shouldn't happen anymore. And at the same time, even also if your crypto breaks silently, at least it should be auditable. You should be able to verify that the stack used is secure. So as a takeaway, if you design protocols, make them auditable. Make sure that the client can verify that the key material used is secure and not chosen badly by the server or by any party. And if you implement some library, check the key material you use. If you get a zero key, maybe reject using that. TLS libraries could fall back to a full handshake and just don't issue tickets under zero key. As mentioned, the artifacts are available, and I'm happy to take questions.